I'm Ryan Poon, and today I will be presenting to the Selective Laser Sintering manufacturing process. An SLS machine is usually comprised of heaters, a build chamber, a powder delivery system, a recoder, a laser, and an XY scanning mirror that directs the laser beam wherever needed. The software first cuts the 3D model into many layers of its cross-section and sends it to the SLS machine, which starts sintering the material layer by layer. The recoder then spreads a thin layer of powder over the platform from the delivery system. The powder is preheated by the integrated heaters to just below melting point, allowing the laser to quickly bond the powders into a solid part. The laser fuses the powder particles based on the model cross-section. Once a layer is successfully sintered, the platform is lowered and the process is repeated. While metal powders can be used, SLS mainly utilizes nylon-based powders such as PA11 and PA12. Comparing the two options, PA11 is superior in flexibility, surface finish, and tensile strength. Additionally, it is produced from renewable resources, which reduces its carbon footprint. While being a cheaper alternative, PA12 has greater heat deflection temperature and operating temperature range. Other materials can also be filled into the nylon powder to create specific properties for applications. Recent developments have allowed for alternatives such as glass-filled, aluminum-filled, or carbon fiber reinforced nylon powders. The advantage of SLS is that unlike any other additive manufacturing process, support structures are not needed to print complex parts with overhangs or hollow spaces. The unfused powders surrounding the sintered parts provide constant support during the printing process. SLS also boasts one of the fastest 3D printing speeds, without significantly compromising quality, which makes it ideal for batch printing. Additionally, SLS parts have high yield and tensile strength. The disadvantage of SLS lie in the high entry cost. While a desktop SLS printer can cost around $5,000, better models can cost around $15,000. SLS also proposes health hazards as the nylon powders that are used have fine particles that can have detrimental health effects if inhaled. Finally, nylon parts printed through SLS are subjected to quick heating and cooling, which can lead to shrinking and warping. Due to how the particles are fused together in the SLS process, the part inevitably has poor surface quality and high porosity, which causes it to be brittle. In order to maximize the potential of the part's properties, post-processing methods are imperative. Vibratory tumbling is a method commonly deployed to improve surface finish and hardness. The part is placed in a container with plastic pellets and subjected to vibratory motions, which ultimately increases the mechanical strength of the component. Here are the micrographs of an SLS printed sample before and after vibratory tumbling. As we can see, there is an improvement in surface finish and reduction in surface porosity.